Hey, honors physics students, here are some hints for the worksheet number 1 and number 2 for chapter 4. This is going to go really fast, so be prepared to click that pause button and I'll just kind of fly through some hints on most of the problems. Worksheet number 1 starts with the woman sliding along, and as you can see, she has a V1 of 5.6 meters per second and she has a V2 of 0 because she's going to stop. So the idea is that if you could find the acceleration by a chapter 2 and 3 formula, certainly it seems reasonable to use the one that I've got illustrated here. Let's get back to that. So in that first, oops, sorry. I'll get back there. V2 squared equals V1 squared plus 2AD. Then after that, why not use net force equals MA? Awesome. The rocket. All rockets blast off from Earth, overcoming gravity. There's no reason why you can't find the acceleration first. But then, notice this formula, this set of force vectors. The upward force is unknown. We don't know what the lift force is, but you're overcoming gravity. That's one of them. If you look at the net force is the subtraction of those. So in terms of writing net force equals ma, the left-hand side is not just one force here. It is the subtraction of force upward minus m times g. Then we simply have to solve for the lift force. Let's jump to number 6. All right, in number 6, there's a forward force of 18 newtons. Notice that it's not accelerating. If it's not accelerating, friction must be exactly the same force of 18 newtons. So if you get a force of friction equals to the coefficient of friction times the normal force, I already gave you the force of friction, that's the 18 newtons. The normal force, recall, on a level surface is m times g. Nice. How about number 7? There's a graph. The graph is a graph of velocity versus time, but the acceleration is the slope of the graph. So for instance, in the first part, if you begin here and go to there, the rise is 20, the run is 4, you get a slope of 5 meters per second squared. That's the acceleration. But by F equals ma, times that by the 2 kilograms, and you get 10 newtons. Look at the first part of the graph. A steady 10 newtons there, because it's a constant acceleration, then a constant force, therefore, and the rest of the graph is for you to fill in. I told you we'd go fast. Number 8, the first part is not intended to be very difficult. You simply use chapter 2 and 3 formulas to find the acceleration in this part. That's not so bad. But if you jump to number 4, to number 8D, the coefficient of friction. For that, I need to draw the force vectors. There is a forward force that I typed in of 2.0 newtons. Friction's unknown to us. We don't know what the force of friction is, but it's resisting. So the net force is what's left over when you take the forward force minus the backward force. Notice how that produces the net force. The net force is the subtraction. Right there, the net force is the subtraction of 2 newtons forward and unknown friction backwards. Well, look, there's only one unknown there. The rest of the problem should fall in place nicely. Jumping to number 9, the skier. The skier is sliding along and slows down, but understand, net force is all the forces put together. However, when you're skiing and you slow down, there is only one force. Therefore, the net force must be the same as the force of friction. So friction, which is slowing down, is a negative force, or it would speed you up. That gives you the acceleration of negative 0.0667. Then what do you do from there? Well, write down the knowns and unknowns. V1 equals 7.0. The unknown V2, and D is equal to 35 meters. The rest should be gentle for you. Number 10. Number 10 is a 26 kilogram mass, Very important. On every ramp problem, there is something that I've labeled F sub P, the force of push or pull caused by gravity, and it always goes down the ramp, 57.3 newtons. In this case, friction is a very large force, and it's trying to stop you. And so the force of friction can be found by, so in this case, the force of friction can be found by using mu times the normal force. So friction is so very large, we have to push downward with an unknown force. So that unknown force, when added to the 57.3 for gravity, which I've called F sub P, must equal the unknown force of friction, and we can find it from there. Jumping to number 11. Yeah, this is a very fun game that all of you have played, I'm sure, at one point or another. But what slides the paper to a stop? It is only friction. So therefore, since you can find friction by mu times the normal force, notice the normal force is mg, but it's got to be in kilograms, not grams. So once you find the force of friction of 0.0368, that is the net force. Again, it's negative because it's slowing you down. That gives you the acceleration. I think I've given you plenty of hints there. However, number 12 is one of those problems where you're pushing with 150 newtons. You're pushing this way, but it's not going to go into the ground. The only part then that makes any difference that actually helps you is the horizontal force of F cosine theta. If you take the forward force of 150 cosine theta, that equals 75 newtons. Certainly from there, we have to include friction, and you can deal with that one. 13 is kind of a tough one because we don't give you the angle. Now notice, gravity pulls straight down. This tension vector right here, here is a tension vector. It is doing two things simultaneously. It is pulling sideways, and it has to pull with 135 pounds, but it has to overcome gravity also. And the force of gravity is 325 pounds. You can find the angle by inverse tangent. After you find the angle by inverse tangent, why not use the only special angle tension formula I've given of mg over sine theta? Well, I might be running out of time, but let's take a look at number 1 on the last worksheet. mg sine theta is pulling down. Every single problem with the ramp has an F sub p going down. For this one, you overcome gravity of mg cosine theta times mu to find the net force for F equals ma. How about the spider? Well, we have a spider web. The upward force is 7.2 newtons. Notice, are you seeing the pattern? I draw vector diagrams each time. The upward force is only this. There are two downward forces, gravity pulling down of mg sine theta and friction of mu mg cosine theta. Combine those, and you'll get the net force for F equals ma. But for part B, there is no tension vector. The tension vector is gone. So there are only two forces, the 3.0, the 3.8, and the 2.0. They are slowing you down, so they have a force vector of negative 5.8. That negative 5.8 allows you to get the acceleration. Chapter 2 and 3 awaits you. Number 4, treat this whole thing as one unit. There is a gravity force of mg sine theta going down the ramp. But because of this force, there's an upward force of 1.96. If you take the 1.96, which is the largest, and subtract the gravity force of this object on the mass and friction, you'll have the net force for F equals ma. So we'll go down now to the second to the last question. You can see the diagram I have here. In this diagram, when you lift with 60 newtons, you are doing two things. You've got a horizontal and a vertical force that you're applying. Okay, so a horizontal and a vertical force. Now recall, the normal force is typically equal to mg on a level surface. However, it's less in this case because you're lifting up. For part B, we are going to use the force of friction since they give us the coefficient of friction, and we know the normal force from the previous problem. Now, this graph helps you figure out how to use F equals ma. And I'm so out of time. So here is just a diagram of the last one. The girl is sledding downward with the thing that I've labeled as F sub p, helped by the wind, hindered by friction. That should help you get F equals ma and go on from there. We're done.